ME 204, Kinematic Equations, Acceleration, Velocity, and Position Relationships. We've talked about velocity and defined an average velocity as a change in position with respect to a change in time. If we have an instantaneous velocity, this is simply a small change in position with respect to a small change in time, or we can define that further as the time derivative of the position function. For acceleration, an average acceleration is the change in velocity with respect to a change in time. An instantaneous acceleration would be the first time derivative of the velocity function. But we know that the velocity function is the first time derivative of the position function. So, instantaneous acceleration can also be defined as the second time derivative of the position function. Let's look at the relationships between position, velocity, and acceleration. If I have a position function defined as 8t cubed plus 2t plus 5, I can find the velocity function by taking the first time derivative. In this case, our velocity would be 24t squared plus 2. I can take the derivative a second time to determine what the acceleration function is. Again, in this case, it would be 48t. Now, what if I had an acceleration function of 3t squared? In order for me to move from acceleration to velocity, I would have to integrate. So the integral of 3t squared would give me t cubed plus c1. Don't forget the constant at the end of integration. This is dependent on our boundary conditions. To move to the position function, I would integrate the velocity function, which would give me 1/4 t to the fourth plus c1t plus c2. Again, remember to include the constant of integration. So how do I find the constants of integration? I have to look at what the initial conditions are. We have an acceleration function of 3t squared, and we have a velocity function of t cubed plus c1. What if the problem said that the object started from rest? That would mean that the initial condition is that the velocity is 0 at time equals 0. If we plug in 0 for the velocity and 0 for the time, then we would find that our constant c1 is also equal to 0. So we would be able to eliminate it from this equation. Now let's look at the position function. We've already eliminated the constant c1 and determined that it was 0 based on our initial conditions. So what if the problem then stated that the object started at the origin? In this case, the position is 0 at time equals 0. So if we put in 0 for position and 0 for time, and solve for the constant c2, we would also find that c2 is equal to 0, and we can eliminate that constant. So the constant of integration depends on our initial condition. If the object did not start from rest, then our constant c1 would have to be some value which would be equal to our initial velocity. And if the object did not start at the origin, then our constant c2 would have to be something other than 0. Let's look at the case of where we have constant acceleration. If the acceleration is constant, and then I integrate that, I get that the velocity is equal to the constant acceleration times the time plus my initial condition, which would be my initial velocity. If I integrate that again to find the position, then I would get 1/2 times the constant acceleration times the time squared plus the initial velocity times the time plus the initial position gives me the final position. These equations make it simple to solve problems that tell us that there is a constant acceleration or when the acceleration is equal to 0. So when we have constant acceleration, our final velocity is equal to our acceleration times the time plus the initial velocity. And our final position is equal to 1/2 times the constant acceleration times the time squared plus the initial velocity times the time plus the initial position. Here's an example. Let's say that the position of a particle is given by the equation s equals t squared minus 3t, where s is in meters and t is in seconds. We want to find the position of the particle at a time of 4 seconds. We also want to find the total distance the particle has traveled at a time of 4 seconds. Well, the equation that we have is a position equation. So if we simply plug in 4 for our time and solve for the position s, we would get that our position at the time of 4 seconds is 4 meters. If we draw that on our little graph, then we can see that at time 0, our position is 0, and at time 4, our position is 4 meters. So does that mean that the total distance that it's traveled is 4 meters? Not necessarily. We have to look at it a little bit closer to determine how far the particle has traveled. For example, what if I put in 1 to my position equation, put in 1 second? If I put in 1 second, then my position turns out to be -2. If I put in 2 seconds, then my position also turns out to be -2. If I put in 3 seconds, then my position turns out to be 0. If I put those in a table and look at those values, I can see that something interesting is happening. The object isn't traveling in a straight line in the positive direction. If I plot what's happening at each of the times that I've calculated, at time 1 we're at -2, at time 2 we're at -2, and at time 3 seconds we're at position 0. By connecting the dots, I can see that the object at some point turns around and goes the other direction. When an object changes direction, its velocity has to go to 0 in order for it to switch directions. So the particle turns around when the velocity equals 0. So how can I find the time that the velocity equals 0? Well, I would need the velocity equation. We know by definition that the velocity is equal to the time derivative of the position function. So if I take the derivative of the position function, that should give me what my velocity is. And in this case, it's equal to 2 times the time minus 3. Now if I set that equal to 0 and solve for the time, I find that at a time of 1.5 seconds, the velocity goes to 0 and the object changes direction. Now I can put that 1.5 back into my position equation and determine the distance that the object travels. So at a time of 1.5 seconds, my position is equal to 1.5 squared minus 3 times 1.5, which is equal to -2.25 meters. So the object travels 2.25 meters to the left, and then travels back 2.25 meters to the right, plus another 4 meters to the right, which gives me a total distance traveled of 8.5 meters. So we have to be careful when we work these kinds of problems to make sure that we understand what the question is asking. Position is different than total distance traveled. Next time, we'll continue our discussion of kinematic equations, acceleration, velocity, and position relationships.